Hello viewers, I'm Kausalya. Today we are going to solve problem number 2 under the topic Nyquist plot. The problem is for a certain control system, a transfer function is given, sketch the Nyquist plot and hence calculate the range of values of k for stability. So in this problem, here we are given a constant k, we don't know the value. Right. So here we are asked to find the range of values of k. For what ranges of k the system will remain stable. Right. So the first step is number of poles lying on the right half of S-plane. So from this problem it is clear, right? The denominator terms represent poles and the numerator term represent zeros. And here we are having 3 poles, right? So here when you equate these 3 terms to 0, we will get the values of poles. So when you equate s equal to 0, so here we will be having s is equal to 0. When you equate this term to 0, what happens? S plus 2 equal to 0, which is nothing but s is equal to minus 2. Similarly, s plus 10 equal to 0, therefore s is equal to minus 10. So when you locate these poles on the S-plane, you see this is our S-plane, right? This is our real axis and this is our imaginary axis. So this is again negative real axis and negative imaginary axis. So now we will locate the poles. So s equal to 0, it will lie here, and s equal to minus 2 here, and s equal to minus 10 here, right? So in the S-plane, all the poles are lying on the left half of S-plane, right? There are no poles on the right hand side. Did you notice that? Yes. So number of poles lying on the right half of the S-plane is 0. So that this is our first step. Then the second step is n is equal to p minus z. So n is number of encirclements and p is number of poles lying on the right half of S-plane and z number of zeros lying on the right half of S-plane. So again, when you look at the problem, you see all the poles are lying on the left half of S-plane. So number of poles lying on the right half of S-plane is 0. And here again in this problem, there are no zeros, right? Because you see there are no numerator terms with s. So here 0 minus 0 becomes 0. So the number of encirclement is 0. So this means that the Nyquist plot should not encircle this minus 1 point. Right. Then step 3 is drawing a rough Nyquist plot. So this is our rough Nyquist plot. Since we are having a pole at origin, here this part, okay, this origin should be bypassed like this. And again, we are splitting the Nyquist plot into different sections. You see, the first section, this is your first section. It starts at plus j infinity and ends at plus j 0. Because this is our imaginary axis, right? And next, this is our section 2. It starts at plus j 0 and it ends at minus j 0. And again section 3, it starts at minus j 0 and ends at minus j infinity. And again your fourth section, it starts at minus infinity and it ends with plus infinity. Right. So this is a method to draw the rough Nyquist plot. Since we are having a pole at origin, here the origin is bypassed. Suppose if you don't have this s term, then you can draw this line straightly. No need to bypass here. Right. And the next step is finding the expression for magnitude and phase angle. So this is our given problem, right? So here initially we are assuming let the value of k be equal to 1. So when the value of k becomes 1, this expression gets modified as 1 by j omega plus 2 and j omega plus 10, right? And the next step is we are going to find expression for magnitude. So how to find the expression for magnitude? We have to take square root as well as we have to square the elements. Both should be done simultaneously. So here we are having j omega. So here we have to take square root as well as we have to square the element present. So what happens? This square root and this square cancels each other. right? So the remaining term is omega here. Again, when you look at this expression, square root of omega square plus 2 square is nothing but 4. So omega square plus 4. Again here, square root of omega square plus 10 square is nothing but 100, right? The next one is finding the expression for phase angle. So phase angle is given by this expression. You see again, look back here. So an omega always contributes an angle of 90 degree. Since I am moving this term to the numerator part, I am including a minus sign. So minus 90 degree. Again, this is a denominator term. I am moving this term to the numerator. So minus tan inverse of imaginary coefficient is omega and the real term coefficient is 2. So omega by 2. Again here, when you move this term to the numerator part, what happens? Again minus tan inverse of omega by 10. Right. So then we are going for section analysis. So here we are considering our section 1. So starting point and ending point. So this is our section 1, right? So what is the starting point? It is plus j infinity. And what is the ending point? It is plus j 0. So just write down the respective values down here. Okay, plus infinity to plus 0. Again, now substitute the value of omega as infinity in the magnitude expression. So once you substitute infinity, what happens? Anything divided by infinity is 0. Again, substitute this infinity value in this phase angle expression. So when you substitute here tan inverse of infinity, it is nothing but minus 90 degree. Again here tan inverse of infinity by 100, again it is nothing but, infinity by 10, again it is nothing but minus 90 degree. So finally we will be having minus 90, minus 90 and minus 90, which is nothing but minus 270, right? And the next thing is we are going to substitute the value of omega as 0. So when you substitute the omega value as 0 here, what about the magnitude? Anything divided by 0 is infinity. So here it is infinity. And again when you substitute the value of omega as 0, minus 90 minus tan inverse of 0 is again 0. And here again tan inverse of 0 is 0. So finally we will be having minus 90 minus 0 minus 0, which is nothing but minus 90 degree. Right. Now we have to find out the value, that is angle or degree of rotation. So here this is the procedure. Minus 90 minus of minus 270. So minus 90 minus into minus becomes plus 270. So minus 90 plus 270 gives you plus 180 degree. What does this plus sign indicates? It indicates the plot is in anti-clockwise direction. Right. Now we are going to draw the diagram for our section 1. Right. So here this is our plot. You see, you know the way to represent the angles, right? So let me tell, but for better clarification you can just look around the video of basics of Nyquist plot. It will make you clear. So here you see 0 degree, and when you move in clockwise direction the angles are negative. You see 0 minus 90 minus 180 minus 270. When you move in anti-clockwise direction the angles are positive. So plus 90 plus 180 and plus 270 degree. So here what is the starting point? The value is magnitude is 0 and the angle is minus 270 degree, right? So this is your minus 270 degree line, right? So here it starts at origin. So it starts at origin and it moves like this. How much angle it should be rotated? It should be moved by plus 180 degree. That is, it should move in anti-clockwise direction. So it is moving like this. This one quadrant covers 90 degree and this quadrant covers another 90 degree. So totally 180 degree. So here you see it starts here, it moves here and it again moves here. Where is it ending? It is ending at minus 90 degree line and it ends at infinity. You see here it is ending at minus 90 degree line, right? Here is minus 90 degree and somewhere it will be ending here at infinity, right? So this is our section 1. The next thing is section 2. What is the starting and ending point of section 2? You see, it starts at plus j0 and it ends at minus j0. So here it starts at plus j0 and it ends at minus j0. Now we are going to substitute these two values in magnitude and phase angle expression. Here when you substitute the value of omega as 0, what happens to the magnitude? Anything divided by 0 is infinity, right? And again when you substitute the value as 0 here, what happens? This tan inverse of 0 is 0 and here also this becomes 0. So the angle will be minus 90 degree. That is, in magnitude is infinity and angle is minus 90 degree. Here we have written that, okay, infinity with an angle of minus 90 degree. Next thing is we have to substitute the value of omega as minus 0. Let's see. When you substitute the value of omega as minus 0, what happens? Again, anything divided by 0 is infinity. Here again when you substitute minus 0, again these two terms becomes 0 and here we are having minus 90. But here there is a special thing which is to be noted. Whenever you substitute the values of plus 0 and minus 0, here in regarding this phase angle, when you substitute minus 0, this angle is modified as plus 90 degree. This is a key point which is to be noted. So here it is plus 90 degree and the magnitude is infinity. Again for calculating the degrees of rotation, so plus 90 minus of minus 90. So what happens? 90 minus of minus 90 is 90 plus 90, which gives 180 degree. Again since it is in plus, so the direction is in anti-clockwise, right? So now we are going to draw. You see, it starts at infinity minus 90 degree, right? So here this is our minus 90 degree line. It starts somewhere at infinity. The angle of rotation is 180 degree anti-clockwise. So here it is rotated in anti-clockwise and 180 degree means we have to cover two quadrants. So this quadrant covers 90 degree and this quadrant covers another 90 degree, right? So totally 180 degree. Where does it ends? It ends in plus 90 degree line and the value of magnitude is infinity. So this is my plus 90 degree line. It ends somewhere at infinity, right? And next one is section 3. So section 3 is nothing but it is the mirror image of section 1. It will be very clear when you look at the rough plot. So you see, this is our section 3, right? And this section 3 is mirror image of your section 1, right? Yes. So no need to again analyze the section 3. Now section 4, here analysis is not needed because it starts and ends at some infinity, right? Minus infinity to plus infinity. So no needed. So next thing is step 5. We are going to find the omega PC and intersection point. For that we have to rationalize the given problem. So here rationalizing is nothing but, you see, this is our given problem, right? So here you see, this is the term which is to be rationalized. So just I am multiplying and dividing this term with the, we can say even it as complex conjugate, but complex conjugate means it should have both real and imaginary terms, but here we are changing the sign for omega also. So not exactly complex conjugate, right? So here this plus j omega, here minus j omega. 2 plus j omega, here 2 minus j omega. Similarly 10 plus j omega and here 10 minus j omega. So we are multiplying and dividing, right? So the next thing is, here just I am combining the numerator terms. You see, k into minus j omega into, I had multiplied these two terms, right? So 10 into 2 gives 20 and 10 into minus j omega is minus 10 j omega. And again when this minus j omega is multiplied with this term, what happens? Minus j omega into 2 gives you minus 2j omega. And again minus j omega into minus j omega gives you minus omega square, right? Now we are going to simplify the denominator terms also. So here you see we are having 2 plus j omega and here 2 minus j omega. So this is of the format a plus b into a minus b. So when you solve, what is the formula? A plus b into a minus b is nothing but a square minus b square, right? So here in the place of a, I am having 2, and in the place of b, I am having omega. So a square is nothing but 4. And again, when you take square for this omega, that gives you, that is j omega into minus j omega gives you plus omega square, right? And similarly 10 plus j omega into 10 minus j omega gives you this answer. So this is our expression. Again, I am multiplying the numerator terms and I am simplifying. You see, multiplication you can do by yourself, right? Just simply multiplying. Minus j omega into 20 minus 20 j omega. Minus j omega into minus j 12 omega. It gives you minus 12 omega square. J into j gives you minus 1. Right, and again here minus into minus becomes plus, and that plus into minus becomes again minus. These are all the basic max terms, okay, you can do. So again finally we are multiplying and we are getting expression like this. And the next step is I am splitting the real and imaginary terms. You see here, what is the real term? Minus 12 omega square is the real term, right? What are all the imaginary terms? Minus 20 j omega plus j omega cube are the imaginary terms. So here you see I am splitting those two terms, and here since denominator is common for both, I am writing the same denominator here for both these terms, right? Yes. Then the next thing is equating imaginary term to 0. So when you equate the imaginary term, this is our imaginary part, right? I am equating it to 0. So what happens? When you move this denominator term to the right hand side, these terms when multiplied by 0 becomes 0. And again here you see I am moving this plus omega cube to the right hand side. So what happens? Here we will be having minus omega cube. This minus and minus cancel each other, and this omega and omega cube cancels, and omega cube becomes omega square. So the value is 20 equal to omega square, and the value of omega is square root of 20. And the next thing is we are going to substitute this omega term in the real term expression. So what is our real term expression here? So this is my expression for real term, right? So here just substitute the value of omega square as 20. Once you substitute the value of omega square as 20, you see after simplifying, here we are having the value of q. This is nothing but intersection point on the negative real axis. This is given as q. So it is given by minus k by 240. So in this problem, we are asked to find the ranges of k, right? So now we are going to do that. So finally, we had drawn our original Nyquist plot or accurate Nyquist plot, right? So we had find out the how to draw section 1, right? This is your section 1 and this is your section 2, and again section 3 is the mirror image of section 1. So this is my section 1, right? So I had drawn exact mirror image of section 1 here. Right, and section 4 is not needed. So this is our final plot. And we had find q, right? Q is nothing but this point on the negative real axis. Right, this is your positive real axis and this is your negative real axis. And what is the value of q? It is given by minus k by 240. Now we have to go back and check our step number 2. So in step 2, what about the number of encirclements? The number of encirclement is 0, right? This should get tallied with our diagram which we had drawn now. So number of encirclement equal to 0. What do you mean by that? Here you see this diagram should not cover the minus 1 plus 0j point. Do you accept? Because here number of encirclements is defined, it is confined to a particular point, right? Minus 1. So for stability by step 2, the number of encirclement is 0, right? So what it means that the diagram which you had drawn should not encircle, should not cover the minus 1 point, or in other words, this minus 1 point should not lie here. For a system to be stable, it should lie somewhere outside, right? So this is the condition. Am I making the concept clear? You see, from step 2, the number of encirclement is 0, right? That is, the value of n is 0. What is mean by that? N is 0 means we should not encircle this minus 1 plus j0 point. So in this diagram, this minus 1 plus j0 point should lie somewhere outside and not within this covered area, right? So for that, what is mean by that? So this value, right, this value should be less than 1. Do you people accept or not? You see, here it is 0 and here it is minus 1, right? Just we are assuming it by ourselves. For stability, this minus 1 should lie outside. Even you can keep here also minus 1, nothing is wrong, right? So here this value, that is this magnitude, or if you measured by using the scale, this distance should be less than 1. Is it right? I am telling that minus 1 should lie outside, or in other words, okay, this distance is less than 1. Both are same, right? If you have 1 here, then this distance is less than 1, right? Same. So here the magnitude of this 0q, it should be less than 1. Since we are considering magnitude, what is this length? What is this 0q? It is nothing but minus k by 240. So just substitute the value here. Since we are considering magnitude, we can eliminate this minus sign. So here we can directly take k by 240, which is less than 1. So what it means? The value of k is less than 240, because when you move this 240 to the right hand side, here k is less than 240. So what is the meaning that for, you see, for the range of k, that is for the system to be stable, the value of k should lie between 0 to 240. Okay, the value of k should lie between 0 to 240, that is it should be less than 240, right? Suppose if you have equal to 240, even equal to also right, but we will stop with this. The value of k should be like k should lie between 0 to 240, right? That's all. The problem gets over here. Hope you people understand well. If you have any doubt, let me know in the comment section. Thank you.